The universe is going to die, not dramatically, not in fire, just quietly. Over an incomprehensible stretch of time, it will run out of things to do. The last star will go dark. The last black hole will evaporate. And then, perfect silence, forever. That was the answer. Then a Nobel Prize-winning physicist looked at that silence and said, "Wait, that is not an ending. That is mathematically identical to a new Big Bang." Roger Penrose believes our universe is one link in an infinite chain, and that the radiation passing through your body right now is older than time itself. If you are new here, welcome to Sundown Science. Get comfortable. Subscribe if this is your kind of thing. You are going to want to stay for this one. Part 1. The ending that should have been final. Picture the last night the universe ever has. Not a night like ours, no stars overhead, no planets turning through their slow ellipses, no light of any kind falling on any surface anywhere, just cold, just distance. Just the long, patient nothing that physics has been building toward since the first fraction of a second after the Big Bang. The last red dwarf burned out so long ago that the number of years since then has more digits than there are atoms in the observable universe. The last black hole finished evaporating, and we will get to exactly how long that takes, because the number is almost insultingly large, and after it went, there was nothing left to structure space at all. No gravity wells, no hotspots, no condensation points, just a near-uniform bath of photons and neutrinos drifting outward through a universe that has been expanding for so long, at so great a rate, that the distance between any two particles is functionally infinite for all purposes that matter. This is what physicists call heat death, and for most of the 20th century, it was considered the final answer to the question of what happens at the end of everything. Not an explosion, not a collapse. Not a dramatic finale of any kind, just a quiet, absolute, mathematically impeccable fade to nothing. The universe runs out of usable energy. Entropy, the tendency of systems to move from ordered states to disordered ones, reaches its maximum value. And once entropy is maximized, once every possible configuration of matter and energy has been fully scrambled into its most probable arrangement, nothing can happen anymore, ever. Physics does not stop. The equations still technically hold, but nothing changes because there is nothing left to change. That is a staggering thought if you sit with it long enough. We are not talking about a very long time. We are talking about a duration so incomprehensibly extended that every unit of time we use to describe human experience, years, centuries, millennia, becomes useless. So let us actually try to walk through the timeline, because the scale of this matters. Right now, roughly 10,000 years into the age of the Milky Way as a galaxy, we are in what cosmologists call the stelliferous era. Stars are forming. Stars are burning. The universe is, by any intuitive measure, alive. But this era has an end date. In about 100 trillion years, that is a 1, followed by 14 zeros, the last star formation event occurs. The raw material runs out. The molecular clouds that gravity normally compresses into protostars have been used up or dispersed, and no new stellar ignition is possible. The last stars that exist at that point are the smallest, coldest, most fuel-efficient ones, red dwarfs. They burn so slowly, so carefully, that a red dwarf with a fraction of our sun's mass can live for trillions of years on its own, but even they go dark eventually. By around 100 trillion years, the last red dwarf flickers out and the stelliferous era ends. What comes next is the degenerate era. The universe is populated with stellar remnants, white dwarfs slowly cooling, neutron stars spinning down, black holes growing fat on anything that wanders too close. This era lasts an almost absurd amount of time. White dwarfs cool toward absolute zero over timescales measured in the quadrillions of years. But eventually, even they go dark, becoming black dwarfs, cold, inert stellar corpses that do nothing but drift. And slowly, over unimaginable timescales, even the protons inside ordinary matter may decay. The theoretical lifetime of a proton, if proton decay is real and we have never observed it, which is its own interesting problem, is somewhere around 10 to the power of 36 years. After that, even the cold remnants of stars dissolve into radiation and a handful of leptons. And then there are the black holes. Black holes are the last complex structures standing. By the time protons have decayed, black holes are the only things in the universe that have any meaningful gravitational influence, any capacity to do thermodynamic work, any claim to being a distinct object rather than a diffuse smear of particles. But Stephen Hawking showed us in the 1970s that black holes are not forever either. They radiate. Very, very slowly. So slowly that a stellar mass black hole takes roughly 10 to the power of 67 years to fully evaporate. And a supermassive black hole at the center of a galaxy takes closer to 10 to the power of 100 years. But they radiate. Hawking radiation bleeds the mass energy out of a black hole particle by particle, and eventually even the largest black hole in the universe completes its evaporation and disappears into a final burst of thermal radiation. 10 to the power of 100 years. Let that sit there for a moment. The current age of the universe is roughly 13.8 billion years, which is about 10 to the power of 10 years. The time it takes for the largest black holes to evaporate is 10 to the power of 100 years. That is not 10 times longer than the current age of the universe. It is not 1,000,000 times longer. The exponent itself is 90 times larger, which means we are talking about a duration that makes the current age of the universe look like the first microsecond after the Big Bang. And after that enormous, staggering, almost insulting duration, the last black hole finishes evaporating, and the universe is left with precisely nothing but a faint, cooling sea of photons, neutrinos, and gravitons spreading outward forever through an expanding space that has no structure and no future. That was supposed to be the end. Physics had a clean answer. Cosmology had a clean answer. Heat death, maximum entropy, no more story. Then Roger Penrose said, "Actually, wait. Penrose, and we will spend a proper amount of time on who he is and why his credentials demand that you take this seriously. Propose something that, when you first hear it, sounds like the kind of thing that belongs in a philosophy seminar rather than a physics paper. He proposed that the infinite far future of our universe is not the end of the story. It is, mathematically and geometrically and physically, the same object as the Big Bang of the next universe. That the heat death, that perfect, empty, radiation-filled final state of everything, is not a termination point. It is a transition surface, a boundary between one cosmic cycle and the next. He calls this framework conformal cyclic cosmology, and he calls each individual universe cycle an aeon. Now, before you dismiss that as metaphysics dressed up in physics language, here is the thing you need to understand. Penrose is not making a poetic argument. He is making a mathematical one. And the mathematics, as we are going to trace through carefully tonight, is rooted in ideas that are already accepted and uncontroversial in physics. Ideas about the geometry of spacetime, about the behavior of light, about what it means to measure time when there are no clocks. The radical conclusion follows from premises that very few physicists would contest individually. It is only when you put them together that the picture becomes something extraordinary. And if Penrose is right, if the mathematics holds and the physics checks out, then the radiation passing through your body right now, the cosmic microwave background that fills every cubic centimeter of space on Earth, may carry within it the faintest compressed afterglow of a universe that lived and died before ours was born. A fossil record of an entire previous cosmic history written in the temperature fluctuations of the sky. That is what we are here to understand. But to get there, we need to start with a problem that predates Penrose, a problem that has been sitting at the foundation of cosmology since the very beginning. And it has to do with why the universe started in such an absurdly improbable state in the first place. Part 2. The problem with forever. Heat death, as an ending, has a philosophical problem that most physics courses skip past because it is uncomfortable and does not have a clean resolution. The problem is this: heat death is not the universe disappearing. It is the universe continuing forever in a state where absolutely nothing happens. Think about what that actually means for a moment. The equations of physics keep running. Time, by some definitions, keeps ticking. Space keeps expanding. The photons in that final radiation bath keep traveling outward. But nothing changes. No complexity forms. No information is processed. No event of any kind occurs, because every event requires an energy gradient, a difference between hot and cold, between ordered and disordered, and heat death is defined precisely as the state where all such gradients are gone. You cannot have a fire without something to burn and somewhere for the heat to go. You cannot have any process of any kind without a difference to drive it, and heat death eliminates all differences permanently. So the universe does not end. It just becomes, for all practical and physical purposes, dead while technically continuing. And forever in this context means an actual forever, not a very long time, but an infinite duration of absolutely nothing happening in a space that keeps expanding into regions no photon will ever reach. If you are the kind of person who finds that deeply unsatisfying, you are in good company. Physicists have a word for this discomfort, though they usually dress it up more formally. The technical version of the unease is this: the equations of physics describe evolution from one state to another. They are extraordinarily good at that. Given an initial configuration of matter and energy, they can, in principle, tell you every subsequent configuration. But they have almost nothing to say about why the initial configuration was what it was, rather than something else entirely. And this is where the heat death problem connects to something much deeper, something that is actually central to understanding why conformal cyclic cosmology exists as a theory. Because the universe did not start in a random state, it started in a state that was, by any rigorous measure, extraordinarily improbable, absurdly, almost impossibly ordered. And a physics that can tell you what happens next, but cannot explain why the story started the way it did, has a significant gap in its foundations. The thermodynamic arrow of time, the reason your coffee cools and does not spontaneously reheat, the reason eggs break but do not unbreak, the reason the past is different from the future, exists entirely because entropy increases. And entropy increases because the universe began in a low entropy state. The past is ordered, and the future is disordered because we started from a point of extreme order. But here is the question that heat death, stretched out to infinity, throws into sharp relief. If the universe ends in maximum entropy, and if maximum entropy is the natural, overwhelmingly probable state for any system, then why on earth did the universe begin in the opposite state? That question has no clean answer in standard cosmology. Inflation, the rapid expansion of the very early universe, explains a great deal about the structure we observe today. It explains why the cosmic microwave background is so smooth. It explains why the universe appears geometrically flat. But it does not explain why the initial conditions that set off inflation were so extraordinarily ordered. And it does not answer the question of what selected those initial conditions from the enormous space of all possible starting points. Penrose's answer, and this is the first hint of where conformal cyclic cosmology is really pointed, is that the question might be circular, that the initial conditions are not arbitrary starting points chosen from some external menu, but the output of a previous cycle. That the universe we observe is not the first universe, and that its improbably ordered beginning is actually the maximally disordered ending of the universe before it, transformed through a geometric process that Penrose argues makes those two states mathematically identical. That is the claim we are building toward, but to understand it, we need to spend some time at the scene of the crime, examining just how extraordinary the initial conditions of our universe actually were. Part 3. The entropy crime scene. Imagine you walk into a room and find a glass of ice water sitting on a table. The ice is not melting, it is actually reforming from liquid water into ice cubes. The room is at normal temperature. Everything is ordinary, except that this one glass of water is running backward, doing something that technically does not violate any fundamental law of physics at the microscopic level, but is so extraordinarily improbable that in any practical sense, it simply cannot happen by chance. That room is approximately the level of improbability at which our universe began, except larger by an amount that makes the glass of ice water look like a guaranteed certainty. The Big Bang did not start in a disordered state. It started in a state of extraordinary, almost incomprehensible order. And most people find this counterintuitive, because when you describe the Big Bang extreme heat, extreme density, everything compressed into a point, it sounds chaotic. It sounds like the most disordered thing imaginable. But thermodynamic disorder is not about how hot or dense something is. It is about how many microstates correspond to the macroscopic configuration you are observing. And the early universe, despite its apparent ferocity, was in a configuration that corresponds to a vanishingly small number of possible microstates. Roger Penrose worked out the numbers on this, and they are among the most jarring figures in all of theoretical physics. To specify the fine-tuning of the initial conditions of our universe, meaning to quantify exactly how special the Big Bang configuration was compared to all other possible ways the same energy could have been arranged, Penrose estimated a probability of approximately 1 in 10 to the power of 10 to the power of 123. That is not 10 to the power of 123. That is 10 raised to the power of 10 raised to the power of 123. It is a number so large that if you wrote out its digits at 1 digit per atom, the number itself would be vastly larger than the observable universe. There is no analogy that does it justice. It is simply beyond the scale of anything that can be physically instantiated as a written number. What this tells us is not that the universe was lucky. It tells us that the universe began in a configuration so special, so far from generic, that luck is not even a meaningful frame. If you selected the initial configuration of our universe randomly from all possible configurations of the same total energy, you would essentially never get what we have. The odds against it are not astronomical. They make astronomical odds look like a coin flip. Now, here is where Penrose's forensic approach gets interesting, because the source of this improbability is not what you might expect. Most people, when they think about the Big Bang as an ordered state, think about the smoothness, the fact that the early universe was remarkably uniform, that the temperature of the cosmic microwave background is the same in every direction to about 1 part in 100,000. And that smoothness does matter. But it is not the deepest source of the fine-tuning problem. The deepest source is gravity. Gravity does something unusual in thermodynamics. For ordinary matter, the high entropy state, the maximum disorder state, is one of uniform distribution. Gas in a box reaches maximum entropy when it fills the box evenly. But gravity flips this logic. When you have a large gravitating system, uniform distribution is not the high entropy state. Clumped distribution is. A universe full of matter that has collapsed into black holes is in a higher entropy state than a universe where that same matter is smoothly distributed because gravity rewards clumping, and the gravitational degrees of freedom, the ways matter can be arranged under gravity, favor collapsed structures over diffuse ones. This means the smooth early universe, which looks superficially ordered, was actually in an extraordinarily low entropy state, specifically because of gravity. It had not yet begun to clump. The gravitational entropy was nearly zero, and the endpoint, the heat-death future, full of evaporating black holes, will have extracted every last unit of gravitational entropy from the matter that once existed in our universe. Penrose has a specific geometric way of describing this. He talks about the Weyl curvature, a component of the spacetime curvature tensor that describes the tidal, shape-distorting aspects of gravity. Black holes have extremely high Weyl curvature. They warp spacetime enormously in their vicinity. The early universe, by contrast, had Weyl curvature extremely close to zero. Penrose's Weyl curvature hypothesis states that the initial singularity of a universe must have Weyl curvature equal to zero, or very close to it, and this is what defines the special, low entropy beginning state that the thermodynamic arrow of time depends on. Now here is something critical to understand. Inflation, the standard cosmological story for how the early universe got so smooth, does an extraordinary job of explaining observational data. The predictions of inflationary models match the cosmic microwave background measurements with remarkable precision. Most cosmologists support inflation, and Penrose does not deny that it works observationally. His argument is more foundational. Inflation does not explain why the pre-inflationary state had the right properties to produce the inflation we observe, and it does not change the overall probability accounting. You still need an extraordinarily special initial configuration to get the inflation off the ground. You have shifted the problem, not solved it. This is an ongoing debate. Physicists like Alan Guth and André Linde, who developed inflationary models, would contest that framing. The argument about what inflation does and does not explain for the initial conditions problem is genuinely unresolved, and it is important to say that clearly. But the entropy accounting that Penrose is doing, the calculation that the Big Bang started in a 1 in 10 to the 10 to the 123 configuration, that arithmetic itself is not seriously disputed. What is disputed is how to interpret it and what follows from it. What Penrose takes from it is this: the initial conditions cannot be arbitrary. Something must select them. And that something, in his framework, is the geometry of the previous aeon, the mathematical structure of what a heat-death universe looks like when you strip away its mass and examine it purely as a conformal geometry. We are going to get to what that means. But first, we need to meet the man who built this framework and understand why, when Roger Penrose says something in physics, even the people who disagree with him pay close attention. Part 4. The Old Man versus the Consensus. Roger Penrose is not a fringe physicist. This is worth saying plainly because when someone proposes a theory as radical as conformal cyclic cosmology, a theory that suggests our universe is one link in an infinite chain of cosmic cycles, that heat-death is a beginning rather than an ending, that we can find fossils of a previous universe in the microwave background of our sky, the natural instinct is to wonder whether this person is operating outside the boundaries of serious science. With Penrose, that instinct needs to be corrected immediately. In the 1960s, Penrose proved, mathematically and rigorously, that the formation of black holes is an unavoidable consequence of general relativity. His singularity theorems, developed in collaboration with Stephen Hawking, established that once a massive enough object begins gravitational collapse, there is no physical mechanism that can stop it forming a singularity. This was not a speculation or a hypothesis. It was a proof. It followed directly from Einstein's equations and some very general assumptions about the nature of matter. It changed the way physics understood both black holes and the Big Bang. Then, decades later, Penrose won the Nobel Prize in Physics in 2020, specifically for the discovery that black hole formation is a robust prediction of general relativity. He was 90 years old when the prize was awarded. The committee was not honoring speculative work. They were honoring work that had shaped the foundations of theoretical physics for 60 years. Penrose also developed twistor theory, an alternative mathematical framework for quantum gravity that reframes spacetime in terms of light rays rather than points, and which has had significant influence on modern mathematical physics. He wrote The Road to Reality, a 1,200-page tour of the mathematical underpinnings of physics that is considered one of the most rigorous popular science texts ever written. He is, in short, someone whose geometric intuition about the deep structure of spacetime has proven reliable in the most demanding possible environments, which makes his skepticism of inflationary cosmology interesting, even if you ultimately side with the mainstream. Penrose has been arguing for decades that inflation is incomplete as a solution to the initial conditions problem, and that the mainstream cosmology community has been insufficiently rigorous about quantifying what inflation actually explains versus what it assumes. This puts him in a minority position among cosmologists. But being in a minority position is not the same as being wrong, and in Penrose's case particularly, history suggests that his geometric intuitions about fundamental physics have a way of turning out to be correct even when they initially seem eccentric. Conformal cyclic cosmology was laid out in full in his 2010 book Cycles of Time, and it has been generating controversy and serious physics papers ever since. It is not a theory that the mainstream has accepted, but it is not a theory that the mainstream has been able to cleanly dismiss either. And the reason for that, the reason it survives serious scrutiny even when individual components are contested, is that its mathematical core rests on ideas that are themselves well-established ideas about the geometry of light, the nature of scale, and the behavior of spacetime at its boundaries. And one of those ideas is so simple and so strange that it is worth spending real time on it. It has to do with the fact that light, in a very precise and technical sense, does not experience time at all. Part 5. The first crack light has no watch. Here is something that special relativity tells us that most people know in the abstract, but have never really sat with long enough to feel the full weight of it. Photons, particles of light, do not experience time. Not experience time differently from us in the way that a moving clock runs slow. Not experience time at a different rate in the way that a clock near a black hole runs slow relative to a distant observer. Photons, travelling at the speed of light through a vacuum, have zero proper time elapsed between any two events on their trajectory. A photon emitted at the moment of the Big Bang, 13.8 billion years ago, that reaches your eye right now, that photon has experienced zero elapsed time between its creation and its detection. From the photon's perspective, if we can anthropomorphize for a moment, it was emitted and detected simultaneously. The entire history of the universe, from beginning to end, occupies no duration whatsoever from the reference frame of a particle travelling at the speed of light. Now, this is not a philosophical claim or a loose metaphor. It follows directly from the mathematics of special relativity, specifically from the definition of proper time. Proper time is the time measured by a clock that travels with an object through space-time, the time recorded on a watch strapped to that object's wrist. For massive objects moving at less than the speed of light, proper time is always positive. It always accumulates. But the formula for proper time involves a term that depends on velocity relative to the speed of light, and at exactly the speed of light, that term goes to zero. Proper time stops accruing entirely. This means photons have no internal clocks. They cannot, in any meaningful physical sense, experience duration. A photon does not age. A photon does not tick. A photon carries no watch. Now ask yourself, why does this matter for a theory about the end of the universe? It matters because of what the far future of our universe is made of. After all the black holes have evaporated, after every massive particle has either decayed or been absorbed, the universe consists almost entirely of photons. Radiation, light. Particles moving at the speed of light, which by definition experience zero proper time, which means the universe in its final state has lost all internal timekeepers. The clocks are gone. Not metaphorically gone physically, thermodynamically, irreversibly gone. The only things left are entities that the equations of physics describe as experiencing no proper time between events. This is not a small technical point. This is the crack in the wall through which Penrose's entire theory enters. If you want to define time physically, operationally define it, not just as a coordinate in some equation, but as something that can actually be measured, you need a clock. And a clock requires a massive object traveling along a time-like trajectory through spacetime. A clock requires something that accumulates proper time, that can compare the reading at one moment to the reading at another. A universe made entirely of radiation has, by the fundamental rules of special relativity, no capacity to measure time at all, not because the clocks have been misplaced, because the physical conditions that allow clocks to exist have ceased to apply. And here is where the first hint of the strange symmetry at the heart of conformal cyclic cosmology appears, though you may not see it yet in full resolution. The early universe, the fraction of a second after the Big Bang, when temperatures were high enough that all particles were effectively massless, when the energy scale was so extreme that the Higgs mechanism had not yet given mass to any particle, that universe also had no effective clocks. The electroweak symmetry was unbroken, particles were massless, and the physics of that moment was, like the physics of the far future, essentially timeless. Two universes without clocks, one at the beginning of the story and one at the end. And if the physics at both ends is structurally identical, if both are dominated by radiation, both are effectively timeless, both exist in a regime where mass plays no role and scale has no physical meaning, then maybe these two ends are not as different as they appear. Maybe, in the precise geometric language of conformal transformations, they are the same thing. But we are getting ahead of ourselves. Before we can follow Penrose through the mathematics of how he stitches end to beginning, we need to understand what it means for scale itself to disappear. Because when there are no clocks, something else vanishes too, and what vanishes is the very concept of size. Part 6. Clocks are not optional. Let us be more precise about what it means to say the far future universe is timeless, because this idea carries more structural weight than it might initially appear to. Time, in physics, is not simply a coordinate. It is not just a number you assign to events so you can put them in order. Physically, operationally, time is what a clock measures. That sounds circular until you define what a clock actually is, and then it becomes profound. A clock is any physical system that cycles or evolves in a regular, reproducible way, such that counting cycles gives you a measure of elapsed duration, a pendulum swinging, an atomic transition oscillating, a quartz crystal vibrating, a pulsar spinning. All of these are clocks because they have massive components undergoing regular motion along time-like trajectories through space-time. The word time-like is technical but important. In relativity, trajectories through space-time are divided into time-like trajectories, the paths of massive objects, which always accumulate proper time, which always move at speeds less than light, and light-like trajectories, which photons travel along, where proper time does not accumulate. The ability to define time intervals to say that 2 seconds have passed, or 2 billion years, requires the existence of systems following time-like trajectories. It requires mass. In the far future universe, after the last black hole has evaporated and the last massive particle has either decayed or been radiated away, there are no time-like trajectories left. Everything is light-like. The universe has become a medium in which only the photon's version of existence is possible, and in that medium, the concept of elapsed time loses its physical grounding entirely. Now, you might wonder whether this matters in practice. After all, time as a coordinate still exists in our equations. We can still write down equations of motion. We can still technically call one moment earlier than another. But here is the subtlety. Without physical clocks, there is no way to calibrate those equations to anything real. The equations contain a time variable, but that variable refers to nothing that can be measured inside the universe. It becomes a ghostly placeholder, mathematically present but physically empty. And the same is true of something else. If you cannot measure time, you also cannot measure distance. Distance measurement, at a fundamental level, requires the ability to time a signal round trip, or to compare a ruler to a standard, or to count cycles of a reference oscillation. All of these methods require clocks, and if clocks are gone, so is the physical content of distance measurements. You cannot say, this object is 1 meter across in a universe with no clocks, not because the ruler is missing, but because there is nothing to define what a meter means as a physical quantity. This is the state Penrose is pointing at when he talks about the far future universe becoming conformally invariant. Conformal invariance means, roughly, that the physics is unchanged when you rescale all distances and times by the same factor. If you double the size of everything and double all time intervals, the physics looks the same. This sounds like an abstract mathematical property, but in the far future radiation-dominated universe, it becomes a physical reality. There is genuinely no physical measurement you can perform that would tell you the difference between a universe of a given size and the same universe scaled up by a factor of 1,000,000. Because the only objects available to make measurements are photons, and photons carry no scale information. This is the thread running through the central claim of conformal cyclic cosmology. If the far future universe is conformally invariant, if it has lost all sensitivity to absolute scale, and if the Big Bang is also, in the appropriate mathematical sense, conformally invariant, then there is a geometric language in which these two states are the same, not similar, not analogous, identical in the sense that a conformal transformation can map one into the other exactly. And if that mapping is mathematically clean, then the question of whether heat death is a termination or a transition becomes a question of which side of a conformal boundary you are standing on. But we are still building the foundation, because to understand how a conformally invariant far future can map onto a conformal Big Bang, we need to understand what the far future actually consists of physically, and why the process of arriving there, the slow cosmic death through black hole evaporation, produces exactly the kind of radiation C that CCC requires. Which means we need to talk about how long it actually takes for a universe full of black holes to go completely dark. Part 7. Scale is an illusion. There is a thought experiment that makes conformal invariance feel real rather than abstract, and it is worth working through slowly. Imagine 2 universes. In the first universe, every particle, every distance, every wavelength of radiation has been scaled up by a factor of 1,000,000 compared to the second universe. The distances between galaxies are 1,000,000 times larger. The wavelengths of every photon are 1,000,000 times longer. Every physical length is uniformly inflated by that same factor. Now ask, Is there any physical measurement you can perform inside one of these universes that would tell you which one you are in? For a universe containing massive objects, the answer is yes. A massive object has a Compton wavelength, a quantum mechanical length scale set by its mass, and that length scale does not scale up just because the universe is bigger. Electrons have a fixed mass, and therefore a fixed Compton wavelength. And if you compare that wavelength to the size of the universe, you get a number that is different in the two universes. Mass gives you an absolute scale reference. Mass is, in a very deep sense, what makes size meaningful. But in a universe with no massive particles, a universe that contains only photons, there is no Compton wavelength to refer to. There is no fixed length scale that persists independently of the overall scaling of the universe. Every length in the photon bath scales together when you apply a conformal transformation, and the physics is completely unchanged. The two universes, the big one and the small one, are, for all physical purposes, identical. Not similar, not analogous. Physically identical, in the sense that no experiment performed inside either universe could distinguish them. This is what conformal invariance means in practice. And Penrose's claim is that this is precisely the state the far future universe reaches, a state where the very concept of scale becomes physically empty, because there are no massive objects to define it. The early universe was in a similar state, though for a different reason. In the first tiny fractions of a second after the Big Bang, temperatures were so extreme that the energy scale of thermal fluctuations vastly exceeded the mass energy of any particle species. Particles were effectively massless, not because they had no rest mass, but because their thermal kinetic energy was so enormous compared to their mass that the mass made no practical difference. The physics was approximately scale invariant. Conformal symmetry was approximately restored. So here is the symmetry that CCC is built on. The far future, cold, dark, radiation only, scale invariant. The early universe, hot, extreme, radiation dominated, approximately scale invariant. Both states exist in a regime where mass plays no role and scale has no physical meaning. Both states are, in the technical sense, conformally invariant or close to it. And conformal invariance is exactly the property you need for the geometric trick at the heart of CCC, the trick that allows an infinite future to be mapped onto a finite boundary that looks like a Big Bang. But notice something. The far future is conformally invariant because everything has cooled and all massive particles have decayed. The early universe is approximately conformally invariant because everything is so hot that mass is irrelevant. These are different physical mechanisms producing the same mathematical property. And for Penrose's theory to actually work for the conformal mapping, to be exact rather than approximate, for the far future to be genuinely, precisely conformal rather than merely approximately. So you need the far future to have gotten rid of all massive particles completely, not mostly, completely. And that is where one of the most speculative and contested pieces of CCC enters the picture. The requirement that mass itself eventually disappears. Part 8. The future becomes pure radiation. Let us walk through the cosmic timeline more carefully than most discussions do, because the details matter here, and the timescales involved carry a kind of narrative weight if you let them accumulate. We are currently about 13.8 billion years into the age of our universe. The universe is dominated by dark energy, which is driving the accelerated expansion we have been observing since the late 1990s. Ordinary matter, the stuff stars, planets, and people are made of, constitutes only about 5% of the total energy content. Dark matter makes up about 27%. Dark energy accounts for roughly 68% and is increasing its share as the universe expands. Over the next tens of billions of years, the Milky Way will merge with Andromeda. Local galaxy groups will collapse under their own gravity while the wider cosmological structure expands away. Eventually, the observable universe from any point will shrink, not because the universe is contracting, but because galaxies beyond a certain distance are being carried away by cosmic expansion faster than light can travel to them. Regions that are currently visible to us will become causally disconnected from us. By around 100 trillion years, all star formation ends. The last red dwarfs begin their extremely slow dimming. From this point on, the universe is in what you might call the long decline, a twilight that lasts far longer than the stelliferous era itself. The fate of protons during this long decline is genuinely uncertain. The standard model of particle physics predicts that protons are stable. It contains no mechanism for proton decay. But many extensions of the standard model, particularly grand unified theories, do predict proton decay on timescales of around 10 to the power of 36 years or more. We have been looking for proton decay in large underground detectors for decades and have never observed it. The experiments keep pushing the lower limit on the proton lifetime higher. Whether protons eventually decay or are stable indefinitely remains an open experimental question, and it matters significantly for the far future of the universe. If protons do decay, then all ordinary matter, every atom that has not been consumed by a black hole, will dissolve into radiation and electrons and positrons within a few times 10 to the power of 40 years. If protons do not decay, white dwarfs and neutron stars remain as cold, solid objects, essentially indefinitely, though they still lose mass over much longer timescales through quantum tunneling processes. Either way, by the time we reach 10 to the power of 67 years, stellar mass black holes have evaporated via Hawking radiation. The mechanism Stephen Hawking identified in 1974, the creation of virtual particle pairs near the event horizon, where one particle falls in and one escapes, effectively drawing mass energy out of the black hole, is so extremely slow at low temperatures that it takes these inconceivable durations to fully drain a stellar mass black hole. For supermassive black holes, the timescale extends to around 10 to the power of 100 years. These are the last complex structures in the universe. After they complete their evaporation, each one releases a final burst of increasingly energetic Hawking radiation as its mass drops and its temperature rises. Black holes, counterintuitively, get hotter as they lose mass, and then they disappear into a final spray of photons, electron-positron pairs, and assorted light particles. After that, the universe contains photons, neutrinos, gravitons, and possibly some residual electrons and positrons from the final stages of black hole evaporation. Depending on the mass of the last black holes to evaporate and the energetics involved, these particles slowly redshift as the universe expands. Their energies drop, their wavelengths grow. They become increasingly dilute and cold. This is the physical state that Penrose needs to examine conformally. A radiation-dominated, nearly massless, scale-invariant sea. And notice, it is almost, but not quite, conformally invariant. Because neutrinos, if they have mass and experimental evidence strongly suggests they do, though the exact values are not fully pinned down, are massive, and massive particles break conformal invariance. This is where CCC requires a step beyond confirmed physics. Penrose speculates that in the extreme far future, the masses of all particles might eventually go to zero, that the Higgs field, which is responsible for giving particles their masses through electroweak symmetry breaking, might relax back to a symmetric state over cosmological timescales. This is not predicted by the standard model. It is speculative physics, but it is physically motivated speculation, not arbitrary addition, and it connects to genuine open questions in fundamental physics about the stability of the Higgs vacuum, which is the next stop on our tour. Part 9. The Forbidden Idea, Mass Switches Off. Mass is not an intrinsic property of particles, the way charge or spin is. This is one of the profound things the Higgs mechanism told us, and it still sounds strange even after you have heard it dozens of times. Before the discovery of the Higgs boson at the Large Hadron Collider in 2012, the idea that mass was a dynamically generated property, that particles acquired mass through their interaction with a quantum field that permeates all of space, was theoretical. After 2012, it became confirmed physics. The Higgs boson is real. The Higgs field is real. And the masses of fundamental particles, the W and Z bosons, the quarks, the charged leptons, arise from those particles' interactions with the Higgs field. In the very early universe, above a certain temperature threshold, the Higgs field was in a state called the symmetric phase. In this phase, the field's value was 0 on average, or, more precisely, the symmetry that the field breaks had not yet been broken, and none of the particles that interact with the Higgs had mass. The universe was in an electroweak symmetric state, all particles effectively massless, physics conformally invariant to a good approximation. Then, as the universe cooled through a phase transition, the Higgs field settled into its current configuration, electroweak symmetry broke, and particles acquired mass. This is called the Higgs mechanism, and it is one of the central pillars of the Standard Model. Now, here is the piece that opens a door to speculation. The Higgs field has not settled into just any configuration. It sits in what physicists call a potential well, a configuration of field energy that corresponds to a local minimum. But the question of whether this minimum is the absolute lowest possible energy state to a true vacuum, or just a local minimum, with a deeper true vacuum somewhere in field space, has profound implications for the long-term stability of the universe. In 2012, when the Higgs boson was discovered with a mass of around 125 billion electron volts, that measurement placed us in a particularly interesting situation. Running the renormalization group equations of the Standard Model forward, essentially, calculating how the Higgs potential behaves at higher energies, the current consensus is that the universe is in what is called a metastable vacuum, not quite a true vacuum, a very deep local minimum, stable for cosmological timescales, but not necessarily the deepest possible state. What this means, in principle, is that a quantum fluctuation, a random tunneling event, could nucleate a bubble of true vacuum somewhere in the universe. This bubble would expand at the speed of light, converting the metastable vacuum of our universe into the true vacuum. Every particle's mass would change. The laws of physics, as we know them, would be different on the other side of the bubble wall. This is the vacuum decay scenario, and it is a genuine theoretical possibility within the Standard Model, though the estimated timescale for spontaneous vacuum decay is vastly longer than the current age of the universe, long enough that it is not a practical concern. Now, Penrose takes this one step further. He speculates, and he is clear that this is speculation beyond established physics, that in the extremely far future of the universe, after all the black holes have evaporated, the Higgs field may gradually relax toward a symmetric state. Not through a violent vacuum decay, but through some gentle, long timescale process that allows the field to drift back towards 0, restoring electroweak symmetry and allowing particle masses to vanish. If this happened, then the residual leptons and neutrinos left over after black hole evaporation would gradually lose their mass. The universe would transition from an approximately conformally invariant state to an exactly conformally invariant state. Scale invariance would be restored completely. The physics of the far future would become mathematically identical in its conformal structure to the physics of the early universe before electroweak symmetry breaking. Let us be absolutely clear here. This is not confirmed physics. The Standard Model does not predict this. There is no established mechanism by which the Higgs field relaxes back to its symmetric state on cosmological timescales under normal conditions. This part of CCC requires physics beyond what we currently have. Penrose acknowledges this. It is the most speculative component of his framework. And yet, it is also not arbitrary hand-waving. It is connected to real open questions about the Higgs vacuum, vacuum metastability, and the long-term behavior of quantum fields in an expanding universe. Whether those open questions resolve in Penrose's favor is genuinely unknown. What matters for the central logic of CCC is this: if mass disappears in the far future, then the end state of the universe is exactly conformally invariant. Scale has no physical meaning, and a conformal transformation can, in principle, map that end state onto the beginning of a new universe. The question is whether the mathematics of that mapping actually works, and whether it produces something that looks like a Big Bang. And answering that question requires a mathematical development that Penrose did not do entirely alone. It required a collaborator named Paul Todd, and a technique called conformal compactification, and a reinterpretation of what the Big Bang singularity actually is geometrically. Part 10. The Mirror, the Early Universe. There is a symmetry hiding in plain sight in the history of the cosmos, and the reason it is easy to miss is that the two ends of the symmetry look completely different in ordinary terms. At the beginning, the universe is hot, dense, and small. Energies are extreme. Temperatures are billions of degrees. The density of matter and radiation is incomprehensible by everyday standards. At the end, the universe is cold, empty, and effectively infinite. Temperatures approach absolute zero. The density of anything is vanishingly small. These two states appear to be each other's opposites in every sense. But in the language of conformal geometry, a language that pays attention only to angles and the structure of light cones, not to distances and durations, these two states have something striking in common. Both are dominated by radiation. Both are approximately or exactly scale invariant. Both are states in which mass plays no essential role. Both are states in which the concept of absolute size has no physical grounding. And both are, in the technical sense, conformally simple states, states where the conformal structure is clean and well-defined in a way that the matter-dominated universe in between is not. This is the mirror at the heart of conformal cyclic cosmology. The early universe and the late universe are, in conformal terms, reflections of each other, not in the sense that the same events happen in reverse, not in the sense that history repeats, in the specific sense that the mathematical description of their geometry, stripped of all scale information, is structurally the same. And if that structural identity is real, if it is not just an approximate similarity but an exact conformal equivalence, then there is a coherent mathematical framework in which the end of one universe and the beginning of the next are not two separate events, but two sides of the same conformal boundary. The question is whether the mathematics of general relativity actually allows you to make this identification cleanly. Can you take the infinite far future of one universe and conformally compactify it, compress it into a finite geometric boundary, and then extend spacetime through that boundary into a new universe? Is that a valid operation in the framework of general relativity and conformal geometry? And the answer, it turns out, is yes, at least mathematically. The person who worked out the details was Paul Todd, and his contribution to CCC is the piece that moved it from a philosophical intuition to a genuine mathematical proposal. Part 11. The Quiet Breakthrough. Paul Todd is a mathematician at Oxford, and in the context of conformal cyclic cosmology, He is the person responsible for the technical heart of the whole framework. The problem Todd addressed was this: the Big Bang singularity in standard general relativity is a place where the curvature of spacetime becomes infinite, where the equations break down, where physics as currently formulated cannot make predictions. It is, in the language of differential geometry, a singularity, a point or surface at which the mathematical machinery of the theory fails. This has always been understood as a fundamental limitation. Penrose himself proved, with the singularity theorems, that general relativity inevitably produces these breakdown points. The Big Bang is one of them. But Todd pointed out something subtle and important. There are different kinds of singularities in general relativity, and not all of them are equally pathological. Some are genuine physical breakdown points, where curvature diverges in ways that cannot be tamed. Others are what mathematicians call coordinate singularities, or conformal singularities. Places where the equations appear to break down not because the physics is genuinely singular, but because of the coordinate system being used. The classic example is the apparent singularity of a black hole event horizon in certain coordinate systems. Switch to different coordinates and the singularity disappears, revealing that it was a coordinate artifact all along. Todd's insight was that the Big Bang singularity might be a conformal singularity of this second type, that if you strip away the scale information, if you look at the space-time geometry of the Big Bang purely in terms of its conformal structure, its angles and causal relationships, rather than its distances and volumes, the singularity might not be a genuine breakdown at all. It might be a smooth conformal boundary, a surface that space-time can be extended through, mathematically, if you work in the right conformal frame. The technical tool for this is called conformal compactification, or sometimes the Penrose diagram technique extended to cosmic boundaries. The idea is to take a spacetime that extends to infinity in some direction, either infinitely far into the future or back to a zero-scale past, and apply a conformal transformation that maps the infinitely extended region into a finite one. The transformation squashes infinity into a boundary, a finite surface that represents all of the infinite future, or the initial singularity, compressed into a geometric edge of a diagram. This is exactly what Penrose diagrams do for individual spacetimes, and Todd extended the technique to the cosmological context in a way that made CCC mathematically precise. What Todd showed is that if Penrose's Weyl curvature hypothesis is correct, if the Big Bang really did begin with Weyl curvature equal to zero, then the initial conformal boundary of our universe is a smooth surface, not a genuine singularity. And if the far future of the previous aeon was in a conformally invariant, radiation-dominated state, then its future conformal boundary is also a smooth surface. And smooth surfaces can be identified with each other. The future conformal boundary of the previous eon becomes, under this mathematical identification, the past conformal boundary, the Big Bang, of the current eon. This is the mathematical move at the center of CCC, and it is elegant in a way that demands respect even from critics of the theory. It does not require exotic new physics. It does not require brains or extra dimensions or quantum gravity. It requires the conformal structure of general relativity that already exists, and a specific claim about initial conditions, the Weyl curvature hypothesis, that is observationally testable in principle. The entire theory is rooted in the geometry of spacetime as we already understand it, applied to boundary conditions that Penrose argues are forced on us by the entropy problem. And this mapping has a consequence that makes CCC not just mathematically interesting, but potentially observationally testable. Because if the far future of the previous aeon contains events, and black hole mergers in particular, are among the most energetically violent events in any universe, then those events leave imprints on the conformal structure of the boundary. And those imprints get carried through the conformal identification into the radiation of the early universe. They show up, if Penrose and his collaborators are right, in the cosmic microwave background. Part 12. The conformal trick. Let us make the geometric argument more concrete, because it is the kind of thing that sounds mystical until you see the mechanics, and then it starts to feel almost obvious in retrospect. A conformal transformation is a smooth change of scale that can vary from point to point, but preserves angles everywhere. The key physical fact about conformal transformations is that they preserve the causal structure of spacetime. Light cones the boundaries of what can causally influence what are preserved under conformal transformations, even when distances and times are rescaled. This means that conformal transformations preserve the deepest structure of spacetime, the web of cause and effect. Now, take the universe in its far future, infinite in extent, filled with radiation redshifted to extremely low energies, expanding forever. Apply a conformal transformation that compresses the infinite future into a finite region. The infinite expansion of the universe gets squashed into a finite boundary surface, the future conformal boundary, which mathematicians call conformal future infinity, or sometimes scri+, written as script I+. In a Penrose diagram, this appears as a diagonal line or surface at the edge of the diagram, representing all of the infinite future compressed into a boundary you can draw on a page. Now, take a Big Bang singularity. In conformal terms, if the Weyl curvature hypothesis holds, and the singularity really is conformally smooth, the initial singularity is also a finite conformal boundary. The expansion of the universe away from the Big Bang, run backward, compresses the entire early universe history into a surface at the beginning of the diagram, the past conformal boundary. Penrose's claim is that these two surfaces, the future conformal boundary of one aeon and the past conformal boundary of the next, can be smoothly identified with each other, geometrically glued together. The infinite future of Universe 1 becomes the Big Bang of Universe 2, not through some dramatic physical process, but through the recognition that they are both smooth, conformal boundaries with matching structure. What crosses this boundary? Only radiation, only massless fields, photons, gravitons, possibly massless neutrinos. Massive matter, every atom, every star, every galaxy, every black hole that has not yet evaporated does not survive the transition. Black holes release their mass energy as Hawking radiation during evaporation, so by the time the transition occurs, all of that energy is in the radiation bath. But the information about the specific arrangement of matter, the history of which galaxy had which structure, which stars were where is encoded in correlations in the radiation bath, not in any surviving massive objects. And those correlations are, in the Hawking radiation model that mainstream quantum mechanics implies, present, but in practice, unextractable. The next aeon begins, from this perspective, not as a point explosion, but as the continuation of a conformally invariant geometry through a smooth boundary. The new universe does not begin at the Big Bang in the sense of starting from nothing. It begins as the conformal continuation of the previous universe's final state, with a new effective scale that emerges as the Higgs-like mechanism of the new aeon kicks in and particles acquire mass again, breaking conformal invariance and establishing a new thermodynamic arrow of time, a new direction of entropy increase, a new complex history. But before it gets there, before the new aeon develops its rich structure, there is a moment at the boundary, the conformal crossing, where the physics of the previous aeon imprints itself on the radiation of the new one. And it is in looking for those imprints that Penrose and his collaborators made the most controversial and most fascinating prediction of the entire CCC framework. Part 13. Eons. Before we get to the observational predictions, let us sit with what this cyclic structure actually implies philosophically, because it is different in important ways from other cyclic cosmologies you may have encountered. An aeon, in Penrose's framework, is not a universe that oscillates. It does not expand, reach a maximum, and collapse back to repeat. There is no big crunch followed by a big bounce. The eons of CCC are not bouncing universes. Each eon expands from its beginning to its heat death without ever contracting. The cycling is not spatial or mechanical, it is geometric. It happens at conformal boundaries, not at turning points. This distinguishes CCC from the ekpyrotic model, where colliding branes in extra dimensions produce cyclic universe events. It distinguishes it from loop quantum cosmology's big bounce scenario, where quantum gravity effects prevent the collapse singularity, and the universe bounces through a minimum size. It distinguishes it from the simple oscillating universe models that were popular in the mid-20th century. In CCC, each aeon is a complete, full universe with its own Big Bang and its own heat death, its own history of structure formation, stars, galaxies, possibly life, eventually black holes, eventually evaporation, eventually conformal flatness, and then the conformal handoff to the next eon. The chain extends infinitely backward and infinitely forward. There is no first eon and no last eon. There was always a universe before this one, and there will always be a universe after the next. What carries information across the boundary? In principle, any radiation that survives to the conformal future infinity of an aeon carries information about the events in that aeon, because Hawking radiation preserves information in the quantum mechanical sense. But there is a critical practical limitation. The information is encoded in correlations among the radiation quanta, subtle quantum entanglements, between specific photons, and those correlations, while present, are so extraordinarily scrambled by the entire history of the aeon that they are, for all practical purposes, unreadable. The next aeon begins in a state that appears almost perfectly thermal, almost perfectly structureless, except for one thing. Black holes do not evaporate quietly in their final states. And the mergers of black holes, particularly the mergers of supermassive black holes at galaxy centers, are among the most energetically powerful events in the universe, releasing more energy in gravitational waves in a fraction of a second than a typical galaxy emits in light over millions of years. Those gravitational wave bursts travel outward from the merger sites, spreading through the universe. And when the universe reaches its conformal future boundary, those gravitational energy concentrations diluted by cosmic expansion, but still present as specific patterns in the radiation field, get compressed through the conformal identification onto the past boundary of the next aeon. They become, in Penrose's words, Hawking points, faint circular concentrations of energy in the radiation bath of the early next aeon universe. And that early radiation bath, after the universe has cooled enough, becomes the cosmic microwave background that we observe today. Part 14. The prediction that changes everything. In 2010, Roger Penrose, working with Vahe Gurzadyan at the Yerevan Physics Institute, published a paper claiming to have found evidence of CCC in the cosmic microwave background data. The cosmic microwave background is the thermal radiation left over from the early universe, specifically from the period about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time. This radiation has been traveling through the universe ever since, redshifted by cosmic expansion to microwave frequencies today, and it fills the sky uniformly in all directions to an extraordinary degree. The temperature variations across the sky, the tiny hot and cold spots that encode the initial density fluctuations of the early universe, have been mapped with extraordinary precision by the COBE, WMAP, and Planck satellite missions. The Planck satellite, in particular, produced a map of the CMB temperature fluctuations with angular resolution and sensitivity that made it possible to look for subtle patterns that earlier instruments would have missed. And it is in the Planck data, as well as the earlier WMAP data, that Penrose and collaborators claimed to find the signatures of CCC. The prediction is specific. If a supermassive black hole merger occurred in the previous aeon, releasing an enormous burst of gravitational energy, that burst would propagate outward as a gravitational wave expanding in a circle from the merger site. When this circular wave pattern gets compressed through the conformal boundary between eons, it should appear, in the CMB temperature fluctuations of our universe, as a circular ring of anomalously low temperature variance. Not a temperature hotspot or cold spot, but a region where the temperature fluctuations are unusually suppressed, unusually uniform in a circular pattern. Penrose calls these Hawking points, named for the Hawking radiation process that ultimately converts the black hole mass into the radiation carrying this signal. The claim made in the 2010 paper, and extended in subsequent work through 2018, is that such circular anomalies have been detected in CMB data at statistically significant levels. The analysis involves looking for circles in the CMB temperature map where the variance of temperature fluctuations is lower than would be expected from the standard inflationary cosmology model, and asking how likely it is that such circles would appear by chance in a sky produced by inflation, with no CCC signal present. Penrose and Gurzadyan's analyses suggested that the circles they found were statistically anomalous, that they appeared with greater frequency and prominence than inflationary simulations would predict. Subsequent work by Penrose collaborators Daniel An, Christoph Meissner, and others extended the analysis and claimed detections of multiple Hawking points at levels of statistical significance between 3 and 5 sigma levels that in physics typically qualify as evidence or discovery depending on the 10 exact value. This is an extraordinary claim. If true, it is direct observational evidence for a previous universe. It would be the most significant cosmological discovery in human history, the first data-driven window into what existed before the Big Bang. But here is where the story becomes an ongoing scientific controversy rather than a settled discovery. Other groups of physicists examined the Planck data using different statistical methods and found that the claimed signals were consistent with what you would expect from ordinary inflationary cosmology without any CCC signal. The circular patterns that Penrose's team identified as anomalous were, according to these counter-analyses, present in LCDM simulations. Simulations based on the standard cosmological model of cold, dark matter with a cosmological constant at comparable rates. The disagreement is not about whether the circles exist in the data. They do. The disagreement is about whether they are anomalous, and that is fundamentally a statistical question about how to properly characterize anomalous in a sky where you are looking for many possible patterns simultaneously. The p-value controversy, the debate about how to correctly calculate the probability that the observed signals are due to chance under the null hypothesis of standard inflation, is technical and ongoing. Different analysis choices lead to very different conclusions. This is not a case where the data clearly resolves the question. It is a case where the data are ambiguous enough that the answer depends significantly on methodological choices that reasonable physicists disagree about. The 2023 and 2024 Planck data releases have not definitively settled the question. The anomalies remain in the data. The statistical debate remains unresolved. And the next generation of CMB experiments is designed to provide the kind of precision polarization measurements that would, in principle, allow a much cleaner test of the CCC prediction. But that brings us to the war over the sky. Part 15. The war over the sky. The debate between Penrose's CCC interpretation of the CMB anomalies and the mainstream statistical explanation can be summarized fairly as follows. Both sides agree on what the data shows. They disagree on what the data means. Penrose's team argues that the circular low-variance rings they identify are too prominent and too numerous to be explained by the standard inflationary power spectrum, and that their characteristics are specifically consistent with the gravitational wave bursts from supermassive black hole mergers that CCC predicts. Counter-analyses by groups including Moss, Scott, and Zibin, as well as others, argue that when proper account is taken of the look elsewhere effect, the fact that you are searching for many possible patterns simultaneously, and that increases your chance of finding a coincidental match, the signals are not statistically distinguishable from inflation. The disagreement is genuine and technical, and it has not been resolved to the satisfaction of either side. The experiments that are coming might change that. Lightbird, a Japanese-led CMB polarization satellite planned for launch in the late 2020s, is designed to measure the large-scale polarization of the CMB with extraordinary precision. CMB S4, a ground-based experiment under development in the United States, targets similar goals. Both are primarily motivated by the search for primordial gravitational waves from inflation, the B-mode polarization signal that would confirm inflationary models. But the same data would provide new constraints on the CCC Hawking point prediction because the polarization pattern of the CMB carries information about the angular distribution of energy in the early universe that temperature maps alone do not fully reveal. If the circular polarization anomalies predicted by CCC are present at the level Penrose's team claims, Lightbird and CMB S4 should see them. If they are absent, that would strongly constrain the theory. Not necessarily falsify it completely, there are always model parameters that can be adjusted but constrain it significantly. The status of CCC in observational cosmology is actively contested, not yet falsified, potentially testable with upcoming experiments, and not accepted by the mainstream, but not dismissed either. The theory is alive in the scientific literature, generating papers, generating responses, generating refinements. That is how science is supposed to work. The thread running through all of this experimental discussion, the reason it matters to the central story we have been telling, is that the CMB is a fossil record. Whether it is a fossil record of the previous aeon or simply a fossil record of the inflationary epoch after our own Big Bang is exactly the question at stake. Either way, the light filling the sky right now is the oldest observable thing in our universe, and it carries information about conditions that no other probe can reach. Part 16. The price of being right. For conformal cyclic cosmology to work for the heat death of our universe to genuinely function as the Big Bang of the next, a specific set of conditions needs to be satisfied. And when you list them all together, the theory starts to look simultaneously elegant and precarious. The first requirement is proton decay. If protons are stable, if they do not decay, then ordinary matter persists indefinitely in the far future universe as cold, inert remnants, black dwarfs, neutron star husks, slowly diffusing atomic nuclei. These massive objects break conformal invariance and prevent the far future universe from reaching the clean radiation-only state that CCC requires for the conformal boundary to be smooth. The standard model says protons are stable. Super Kamiokande and other experiments have been searching for proton decay for decades without finding it. If proton decay is not real, CCC has a serious structural problem. The second requirement is the disappearance of mass. Even if protons decay, neutrinos appear to have small but non-zero masses. Electrons and positrons produced in the final stages of black hole evaporation have masses. For the universe to reach a truly conformally invariant state, all massive particles need to either annihilate or have their masses go to zero. The mechanism Penrose proposes, the Higgs field, relaxing back to its symmetric state, is speculative and not supported by the Standard Model. The Standard Model does not predict this. For this requirement, CCC needs physics beyond what we currently have confirmed. The third requirement involves the information paradox. The standard interpretation of Hawking radiation, going back to Hawking's original calculations, is that the radiation is perfectly thermal. It carries no information about what fell into the black hole. Under this interpretation, information is destroyed in black holes, which is in tension with quantum mechanics and its fundamental requirement that physical evolution preserve information. Most modern theoretical work on black holes, informed by string theory and holography, strongly suggests that information is actually preserved, that Hawking radiation is subtly non-thermal in a way that allows recovery of the initial state in principle, though not in practice. If information is preserved, if unitarity holds, as it does in the most sophisticated current models, then the radiation that fills the far future universe actually carries all the information about the matter that formed every black hole in cosmic history. The radiation is not a featureless thermal bath. It is a fantastically scrambled but complete encoding of all the matter history of the universe. Whether this is a problem for CCC depends on whether that scrambled information can still produce a smooth conformal boundary. The relationship between information preservation and conformal smoothness in Penrose's framework is an open technical question. The fourth requirement is a stable, positive dark energy, a cosmological constant or something that behaves like one, driving the eternal expansion of the universe into a de sitter future. The conformal structure of CCC, particularly the properties of future conformal infinity, depends on the universe expanding into a de sitter-like geometry. If dark energy is not constant, if it weakens over time, or if it changes sign and causes the universe to eventually contract, the conformal structure changes and the CCC framework may not apply. Recent data from the DESI survey has suggested hints that dark energy may be evolving, not constant. If that result holds up with more data, it would create tension with the CCC assumption of a stable cosmological constant. Each of these requirements is either uncertain, contested, or requires physics beyond the Standard Model. Taken individually, none of them is implausible. Taken together, they paint a picture of a theory that is internally elegant and externally fragile, dependent on multiple conditions, each of which could independently fail, and which together represent a very specific portrait of how the universe works at its most extreme limits. Penrose would say, and does say, that the elegance of the geometric framework is evidence in its favour. That theories which simplify the problem of initial conditions deserve serious consideration, even if they require extensions of current physics. His critics would say that elegance is not evidence, and that a theory requiring 4 separate, unconfirmed assumptions to function is doing a lot of work with very little observational scaffolding. Both positions are intellectually defensible. The theory is not proven. The theory is not dead. Part 17. The other endings waiting in the dark. Conformal cyclic cosmology is not the only alternative to heat death that theoretically rigorous physics can offer, and it is worth understanding the landscape of possibilities not as an exhaustive survey, but to calibrate exactly what kind of claim CCC is making and where it sits among its competitors. The Big Rip is perhaps the most dramatic alternative ending. In the standard cosmology, dark energy has a fixed energy density described by the cosmological constant. But if dark energy is actually a dynamical field called phantom energy, with a parameter called the equation of state W that is less than -1, then the energy density of dark energy increases over time rather than remaining constant. An increasing dark energy density drives increasingly rapid expansion, and eventually the expansion becomes so fast that it tears apart gravitationally bound structures. First galaxy clusters are ripped apart, then galaxies, then solar systems, then planets, eventually atoms, and finally spacetime itself dissolves in a singularity of infinite expansion rate. This big rip would end the universe in a finite time current estimates, depending on the phantom energy model, put it anywhere from 20 billion to 200 billion years from now. The big rip does not produce a conformal boundary. It produces a genuine singularity. CCC has no mechanism to operate in a big rip universe, because the conformal structure that allows future infinity to be a smooth surface depends on the universe expanding into a de Sitter-like geometry, not tearing apart. Vacuum decay is another possibility that standard physics takes seriously. If the Higgs vacuum is indeed metastable, sitting in a local but not absolute minimum of the Higgs potential, then a quantum tunneling event could nucleate a bubble of true vacuum. This bubble would expand at the speed of light in all directions, converting everything it reached to a region with different physical constants, different particle masses, different laws of physics. This would not be an ending in the ordinary sense. There would be no gradual decline, no era of increasing entropy, just an expanding bubble wall of altered physics arriving with no warning. Vacuum decay is a possibility that exists within the standard model, requires no additional assumptions beyond the observed Higgs mass, and has no connection to CCC. A vacuum decay ending would preclude the conformal boundary structure CCC requires. Loop quantum cosmology offers an approach in which the quantum geometry of spacetime at the Planck scale, the scale where general relativity is expected to break down and quantum gravity effects become significant, provides a natural repulsion that prevents singularity formation. In this framework, the Big Bang is actually a big bounce. The universe contracted from a previous phase, reached a minimum volume at the Planck density, and then began expanding again. The contracting phase was the universe before ours in this picture. This is a genuine cyclic cosmology, but different from CCC in important ways. It requires quantum gravity physics rather than conformal geometry. It involves a contracting phase that CCC lacks, and it does not naturally address the entropy problem in the way CCC attempts to. Eternal inflation, associated with André Linde and Alan Guth, among others, suggests that the inflationary process that drove the early universe's expansion never fully ends on large scales. While inflation ended in our local region to produce the observable universe, quantum fluctuations in the inflaton field can keep inflation going eternally elsewhere, constantly nucleating new bubble universes. In this picture, our universe is one of an infinite number of bubble universes embedded in an eternally inflating background. This is cyclic, in a different sense. There is always another universe being born, but it shares no geometric structure with CCC and does not address the entropy problem via conformal boundaries. What distinguishes CCC from all of these, and what gives it its particular character in the space of cosmological theories, is that it attempts to solve the initial conditions problem, the extraordinarily fine-tuned, low entropy, beginning through a concrete geometric mechanism. The other theories either ignore the problem, sidestep it, or address it through different mechanisms. CCC is the only theory that directly proposes that the special initial conditions of our Big Bang are determined by the geometry of the previous aeon's ending. That is an ambitious project, and it is why the theory deserves the serious examination it continues to receive. even as individual components remain unconfirmed. Part 18. The signal problem. Here is a question that is worth asking, even if you are fairly certain the answer is going to be disappointing. If conformal cyclic cosmology is correct, and if each eon leaves imprints on the next through the conformal boundary, could a civilization in a previous eon have intentionally encoded a message in those imprints? Could whatever intelligence might have existed in the universe before ours have known about the conformal transition and attempted to leave information for the next aeon? Could someone, somewhere, in a cosmos that burned and died before ours was born, have looked at the mathematics of their own ending and thought, there is a door here, and something is going to walk through it, and maybe we can say hello? The answer, in practice, is almost certainly no. But the reasoning for why not is interesting in its own right, and working through it tells you something genuinely important about the nature of information, the structure of the conformal boundary, and just how extreme the physical constraints on any civilization, no matter how advanced, actually are. Start with what crosses the boundary. The information that survives the conformal transition is carried in the radiation field, specifically in the detailed quantum correlations among the photons and gravitons that make up the radiation bath of the far future universe. In principle, this is extraordinarily rich. Every photon carries phase information, polarization information, directional information. The full quantum state of the radiation field encodes, in its correlations, the entire history of everything that ever happened in that aeon. Every star that ever burned, every black hole that ever formed and evaporated, every merger, every collision, every particle interaction going all the way back to that aeon's own Big Bang, all of it, in principle, recoverable from the quantum state of the radiation. But here is where the engineering problem begins to reveal its true scale. By the time a universe reaches its conformal future boundary, the radiation has been expanding and redshifting for timescales of 10 to the power of 100 years or more. Let that sink in. 10 to the power of 100 years. The current age of our universe is approximately 10 to the power of 10 years. We are talking about a duration that makes our entire cosmic history, from Big Bang to today, look like the first microsecond of existence. Over that incomprehensible span of time, the wavelengths of photons have been stretched by factors that make the entire expansion of the observable universe since our own Big Bang look infinitesimal by comparison. The energy of each individual photon is, for all practical purposes, zero, not low, not faint. Effectively, functionally, thermodynamically, zero. And the quantum correlations that encode information, the subtle entanglements between photons that, in principle, carry the history of the aeon, are spread across spatial scales that make the entire observable universe today look like a single atom in comparison. The information is there, technically. The physics of unitarity says it has to be, but it is distributed across volumes so enormous, in correlations so delicate, that extracting any meaningful portion of it would require an act of measurement that is, by any standard we can imagine, physically impossible. Now ask what it would take to deliberately encode a message into that radiation field. Not just leave an accidental imprint, but actually structure the quantum state of the radiation in a way that produces a detectable, decodable signal in the next eon's early universe. You would need to manipulate the radiation field coherently on scales that span the entire observable universe of your aeon. Not your galaxy, not your galaxy cluster. The entire observable universe, hundreds of billions of light years across. You would need to coordinate the quantum states of photons separated by billions of light years from each other, imposing specific phase relationships, and polarization correlations across distances that light itself, traveling for the entire age of your universe, could barely connect. You would need to do this with the precision of a quantum computer operating at cosmic scales. And you would need to do it near the end of your universe's life, in the deep future, when the thermodynamic constraints on doing any kind of work at all are at their most brutal, when the available energy gradients have been reduced to nearly nothing, when the universe is at its most hostile to anything resembling organized effort. This is where the Kardashev scale becomes useful as a reference point, even though it was never designed with this kind of problem in mind. A Kardashev Type 1 civilization harnesses the total energy output of its home planet. Type 2 harnesses the full output of its star. Type 3 harnesses the energy output of an entire galaxy, something like 10 to the power of 44 watts continuously. That sounds like a lot. It is a lot. But the scales required for aeon-to-aeon communication are roughly 9 orders of magnitude larger than what a Type 3 civilization can access. You would need something like a Type 5 civilization, a hypothetical category that does not even appear in most discussions of the Kardashev scale because it is so far beyond anything grounded in plausible physics, a civilization harnessing not a galaxy but the entire observable universe, coordinating engineering across billions of light years simultaneously, operating under the thermodynamic constraints of a universe in its final stages of dying. And even then, even if you somehow achieved that, the signal you encoded would be compressed through the conformal transition into an imprint so faint that distinguishing it from the natural statistical noise of the radiation bath would require the receiving civilization, us, potentially to have already solved the very measurement problems that make reading Hawking radiation in the first place essentially impossible. So the honest answer is this: no, a previous civilization almost certainly could not have left us a deliberate message, not because the physics forbids it in principle. The physics is actually somewhat agnostic about it. But because the engineering gap between what any physically realizable civilization could do and what the task actually requires is not a gap of degree, it is a gap of kind. It is the difference between building a tall tower and building a structure that reaches the moon with your bare hands. What does cross the boundary, and what we might actually be able to detect, is something far more humble and far more interesting. The unintentional imprints, the gravitational wave signatures of supermassive black hole mergers that occurred in the previous eon, whose energy patterns were compressed through the conformal transition and imposed themselves on the radiation of our early universe. The statistical fingerprints of large-scale structure, the way matter was distributed on the largest scales in the previous cosmos, reflected faintly in the temperature fluctuations of our own cosmic microwave background. These signals were not sent. They were left the way a footprint is left in concrete that has not yet set, without any intention, simply because something heavy was there at the right moment. These are not messages. Nobody addressed them to us. Nobody knew we would be here to receive them. They are fossils. And fossils, as any paleontologist will tell you, can tell you an enormous amount about what came before, about the scale of the creatures that walked, the environment they lived in, the events that shaped their world if you know how to read them. The entire discipline of paleontology is the science of reading unintentional records, of extracting history from impressions that were never meant to be history at all. And that is exactly what Penrose and his collaborators are attempting when they analyze the CMB sky for Hawking points. They are not listening for a message. They are reading a fossil record. They are looking at the oldest observable thing in our universe and asking whether, underneath the expected pattern of inflationary fluctuations, there are circular impressions left by the gravitational signatures of a universe that died before ours was born. The previous aeon did not know we were coming. It could not have known, but it was there, and it was heavy, and the concrete was still wet. Part Ninetine, the room you're sitting in. Stop for a moment and consider the space you are actually occupying right now. Not the space in the abstract philosophical sense, the literal physical volume of air around you, the cubic meters of room that your body is sitting or standing inside at this exact moment. Because that space is not empty, it is not even close to empty. It is one of the most crowded places in the universe in terms of the sheer variety of electromagnetic radiation passing through it simultaneously, and most people go their entire lives without registering any of it. Start with the obvious. Visible light is here, bouncing off surfaces, entering your eyes, carrying information about the shape and colour of everything around you. But visible light is a tiny sliver of the electromagnetic spectrum, a narrow band of frequencies that your visual system happened to evolve sensitivity to, because those are the frequencies the sun outputs most abundantly and the atmosphere transmits most cleanly. Outside that narrow band, in every direction of the spectrum, the room is equally full. Radio waves are passing through your walls right now. Dozens of them, hundreds of them, carrying encoded signals from broadcasting towers and cell towers and satellites in orbit. The walls of your room are essentially transparent to most radio frequencies. The signals from stations broadcasting hundreds of kilometers away are here, in this room, at this moment. You are sitting inside a radio receiver that you cannot tune, slightly higher in frequency, microwaves from your local wireless network, bouncing between router and device, filling the room with a constant structured electromagnetic field. Higher still, infrared radiation from every warm object in your vicinity, your own body radiating it continuously, the walls absorbing and re-emitting it, the whole room in a slow thermal conversation conducted entirely in wavelengths your eyes cannot detect. Higher still, ultraviolet from whatever sunlight leaks in, and filtering through from outside the Earth entirely, faint but present, X-rays from energetic cosmic sources, gamma rays from radioactive decay in the ground and the walls and your own body. The room is not a quiet place. It is an extraordinarily busy intersection of electromagnetic signals, and you move through it completely unaware of most of what is there, because you only have instruments for one narrow frequency band built directly into your skull. But all of that, every radio wave, every infrared photon, every Wi-Fi signal, every X-ray filtering down from the sky is local, recent, generated by nearby sources in the last fraction of a second or the last few years. Those signals are young. They carry information about the present state of the world around you. What is not local, what is not recent, what is in a completely different category from everything else filling this room is the microwave background. The cosmic microwave background is not a distant wall of light sitting at the edge of the observable universe. That is a common misunderstanding worth correcting carefully, because the reality is stranger and more immediate. The CMB is here, in this room, right now. Microwave photons from the cosmic background are passing through your body at this moment at a rate of hundreds of millions per cubic centimeter per second. They are not arriving from one direction. They are arriving from every direction simultaneously with almost perfect uniformity because they fill the entire universe homogeneously. Every cubic centimeter of space anywhere in the observable universe contains the same bath of CMB photons that your room contains. It is the most pervasive form of radiation in the cosmos. And these photons are old in a way that no other radiation you will ever encounter is old. They have been travelling since 380,000 years after the Big Bang. To put that in perspective, the universe is currently about 13.8 billion years old. These photons began their journey when the universe was less than 3/100% of its current age. They were created in the moment the universe first became transparent, the moment the primordial plasma of protons and electrons cooled enough to combine into neutral hydrogen atoms, allowing light to travel freely for the first time in cosmic history. Before that moment, the universe was opaque. Photons could not travel more than a tiny distance before being scattered by the charged plasma. After that moment, the photons that were present at the transition streamed freely outward in all directions, and they have been traveling ever since, for nearly 14 billion years, without interacting with anything significant. They carry the imprint of conditions at that transition moment, the slight variations in temperature and density that existed across the primordial plasma, unmodified by any intervening absorption or emission. They are a direct, unprocessed record of the early universe, as faithful as a photograph taken the moment the universe first became visible. No telescope, no instrument, no observation we make of distant galaxies or ancient quasars comes close to looking back as far as the CMB. When we look at the most distant galaxies with our best space telescopes, we are seeing light from a few 100 million years after the Big Bang. The CMB is from 380,000 years after the Big Bang. It is by far the oldest observable thing in our universe, and it is not sitting at some remote distance. It is here, in your room, passing through you. Now take that fact, that ancient, intimate, pervasive fact, and add Penrose's interpretation onto it. Because if conformal cyclic cosmology is correct, then the age we just assigned to those photons is not their full age. 380,000 years after our Big Bang is when they were last scattered. But the energy that produced them, the radiation field that they are part of, did not begin at our Big Bang. It crossed through the conformal boundary from the previous aeon. It is, in Penrose's framework, radiation that predates our universe entirely. The temperature fluctuations encoded in the CMB, those slight variations in intensity from one direction to the next, 1 part in 100,000, the tiny ripples that seeded all the large-scale structure of the universe we observe contain, compressed within them, the afterglow of events that happened in the universe before ours. Supermassive black holes merging in a cosmos that burned and died before our Big Bang. The gravitational energy of those mergers travelling outward through that previous eon, reaching its conformal boundary, crossing through, and imprinting itself as circular patterns of anomalously low temperature variance in the radiation of our early universe. The photons in your room are, if Penrose is right, carrying postal marks from a previous cosmos. Now, the honesty part, because this is important and it would be wrong to skip over it. This is not confirmed. The Hawking point signals that Penrose and his collaborators claim to have found in the CMB data are disputed by other physicists using different statistical methods. The question of whether those circular low-variance rings are genuinely anomalous, genuinely inconsistent with what standard inflationary cosmology predicts, or whether they are simply what you would expect to find if you look hard enough at any sufficiently large dataset, has not been definitively resolved. The conformal boundary mechanism that CCC proposes depends on several physical assumptions: proton decay, mass eventually vanishing, specific properties of dark energy that have not been confirmed experimentally. The mainstream cosmology community is, at best, skeptical and, more accurately, largely unconvinced. There is a real possibility, perhaps even a likelihood by the weight of current opinion, that the CMB fluctuations passing through your room are exactly what standard inflation predicts. Random quantum fluctuations from the inflationary epoch, imprinted on the primordial plasma, nothing more and nothing less. Extraordinarily interesting in their own right, carrying a wealth of information about the first fractions of a second of our universe, but carrying nothing from before our Big Bang, because there was no before our Big Bang in any physically meaningful sense. But there is also a possibility that they are not. And the reason that possibility deserves serious attention rather than dismissal has nothing to do with Penrose's reputation or the elegance of his mathematics, because neither of those things is evidence. The reason is structural. CCC makes a specific, quantitative, testable prediction about patterns in a real dataset that already exists and can be analyzed. It is not a vague claim about the universe being cyclic in some philosophical sense. It is a claim that says, look at the CMB data, look for circular rings of low temperature variance at specific angular scales, and you should find more of them, and stronger ones, than the standard model predicts. That is the kind of prediction that science can actually engage with. It is falsifiable. It is being tested. The answer is not yet in. Think about what it would mean if the answer came back yes. The radiation filling your room would not be old light. It would be light from before the beginning. Not the beginning of our universe, the beginning of time as we have ever defined it. Every moment you have ever stood outside and looked at the night sky, every time you have ever used a microwave oven and watched it heat your food, every morning you have ever woken up, and the first photons of the day have fallen on your face. In all of those moments, you have been in the presence of radiation that, if Penrose is right, has been travelling since before our Big Bang. Since a universe you will never observe directly, populated by matter you will never characterize, structured by a history you will never reconstruct, came to its ending and handed its radiation across a conformal boundary into the beginning of ours. The photons in your room are not just old, they are potentially survivors. And the universe they survived is not a metaphor or a philosophical abstraction. It was a real place, as real as this one, that simply ran out of time and left the light on for whoever came next. Part 20. The Handoff. Let us end at the boundary itself, because that is where everything converges. Imagine you could somehow observe the conformal future infinity of a dying universe, not from outside it, because there is no outside, not from a distant vantage point, because distance requires space, and space requires scale, and scale requires mass, and none of those things exist at this boundary. Imagine instead that you could somehow be present at the geometric surface that represents the endpoint of all structure, the place where time and scale and distance lose their physical meaning entirely and the universe arrives. After an incomprehensible duration, at the only state it was always moving toward, what would it look like? Not visually, because visual experience requires eyes, and eyes require brains, and brains require neurons, and neurons require chemistry, and chemistry requires atoms, and atoms require protons that have long since decayed, and electrons that have long since annihilated with their antimatter partners and been radiated away as photons. The biological and physical infrastructure of anything we would recognize as an observer does not survive to this point. Nothing massive survives to this point, so we cannot ask what it looks like in any ordinary sense. But we can ask what it looks like geometrically, mathematically, structurally. We can ask what kind of object it is in the space of all possible spacetime configurations, and the answer is precise. It is a surface. A smooth, curved, conformally flat surface in the mathematical space of all possible spacetime geometries, not a wall, not an edge. A surface in the technical differential geometry sense, a boundary that the manifold of spacetime approaches asymptotically, a limiting structure that encodes in its geometry everything that the universe became over its entire history. On one side of this surface is the infinite future of a universe that has been running for a duration so large that writing the number in standard notation is not possible. A universe that spent the first few billion years making galaxies, the next 100 trillion years burning through stellar fuel, The next unimaginable stretch of time, slowly dissolving its matter through proton decay and black hole evaporation. The next stretch of time, even longer than that, converting every last black hole into a final spray of Hawking radiation, and then cooling, expanding, redshifting, until the last photon's energy dropped to effectively zero, and the universe arrived at its final, maximally disordered, perfectly featureless state. All of that history, every star that ever burned, every planet that ever formed and was eventually swallowed, every civilization that ever arose and went extinct, every black hole that ever devoured matter and slowly returned it to the universe as radiation, every photon that ever scattered off every electron in the entire history of the cosmos is encoded somewhere in the quantum state of the radiation field that ends at this surface, not lost, not erased. Encoded in correlations so complex and so dilute that no physical process inside the universe could ever decode them. Present but inaccessible, a complete record that nobody can read. On the other side of the surface is nothing. And it is important to be precise about what kind of nothing, because there are different kinds of nothing and they are not equivalent. The nothing on the other side is not the nothing of empty space. Empty space is a physical state. It has a geometry, a vacuum energy, quantum fields humming at their ground states, virtual particles flickering in and out of existence. Empty space is full of structure in the quantum field theory sense. The nothing on the other side of the conformal boundary is more radical than that. It is the nothing of a spacetime that has not yet been specified, a blank in the mathematical description of reality. The other side is whatever comes after, and nothing about the physics of our universe constrains what that means until you apply the conformal matching condition, until you say that the geometry of the new beginning must match the geometry of the old ending at the boundary surface. And in Penrose's framework, when you apply that matching condition, what you get on the other side is the beginning of the next aeon, a new spacetime that picks up where the conformal surface left off. A new universe that inherits the conformal structure of the previous universe's ending and uses it as its initial condition. A universe that starts in a state of extraordinarily low gravitational entropy because the Weyl curvature of the conformal boundary is forced to zero by the smoothness of the matching surface. And zero Weyl curvature is precisely the special initial condition that Penrose's Weyl curvature hypothesis identifies as the source of the thermodynamic arrow of time. The new universe begins ordered, not because it was lucky, not because something outside it selected a special initial configuration from an enormous menu of possibilities, but because the geometry of the transition forced it to. The boundary surface has only one allowed curvature. The new beginning has only one allowed starting geometry. The apparent fine-tuning is not fine-tuning at all. It is a constraint. This is the central claim of conformal cyclic cosmology, and it is worth sitting with it for a moment without rushing to evaluate it, because it is genuinely elegant in a way that deserves appreciation regardless of whether it is correct. The deepest problem in cosmology, why did the universe begin in a state of such extraordinary, almost impossible order, is answered not by appealing to a selector, not by postulating a multiverse that samples all possible initial conditions, not by invoking an anthropic principle that says we necessarily find ourselves in a universe with the right properties for observers to exist. It is answered geometrically. The universe began ordered because the thing it was born from was conformally flat at the boundary, and conformal flatness at the boundary means Weyl curvature equals zero, and Weyl curvature equals zero means low gravitational entropy, and low gravitational entropy means a thermodynamic arrow of time points forward, and a thermodynamic arrow of time pointing forward means structure can form. Stars can burn, planets can cool, chemistry can happen, and here we are having this conversation. The entire chain of causation that led to your existence, traced all the way back, terminates not at a random quantum fluctuation or a lucky initial condition, or a divine selection from the space of all possible universes, but at a conformal boundary surface that could not have been anything other than what it was, because the geometry of the previous aeon's ending allowed no other option. Now the chain of eons extends infinitely in both directions, and this is one of the philosophically strangest implications of CCC, the one that most fundamentally rearranges your intuitions about time and beginning and existence. There was a universe before ours. There was a universe before that one. There was a universe before that one. Going back, aeon by aeon, with no first aeon, no original universe, no moment at which the chain started from nothing. Each aeon begins in the low entropy state, the conformal transition in forces, builds its structure, burns its fuel, evaporates its black holes, reaches its conformally invariant ending, and hands off. Each aeon is complete, self-contained, finite in duration from the inside. And each aeon is one step in a process that has no beginning and no end, a relay that has always been running and will always run, in which no single runner is the first or the last. There is no creation event in this picture. There is no moment at which something came from nothing. There is only the endless conformal handoff, universe to universe, each one dying into the beginning of the next, each death as quiet and geometrically inevitable as the one before it. You should hold all of this with appropriate epistemic humility, and Penrose himself would insist on it. CCC requires proton decay, which decades of dedicated experimental searching have not found. It requires that particle masses eventually go to zero, a process the Standard Model does not predict and for which there is no confirmed mechanism. It requires a specific relationship between information preservation in black hole evaporation and the smoothness of the conformal boundary that has not been worked out to everyone's satisfaction, and which sits in tension with the mainstream understanding of unitarity in quantum mechanics. Its primary observational prediction, the Hawking points in the cosmic microwave background, the circular rings of low temperature variance left by black hole mergers in the previous aeon, is disputed by other groups of physicists who find the same patterns consistent with standard inflation when proper statistical accounting is done. None of this is settled. All of it is contested. Penrose is clear about this in his own writing. The conformal mathematics, the geometric framework, the compactification technique, the boundary identification is solid. That part builds on well-established differential geometry and uses tools that the physics community has accepted for decades. The physical requirements attached to the mathematics are the contested part. Whether the physics actually satisfies the geometric requirements of CCC is exactly the question that experiments over the next decade are designed to probe. Lightbird, the CMB polarization satellite, will provide precision measurements of the large-scale polarization structure of the microwave background that should allow a much cleaner test of the Hawking point prediction than current data allows. CMB, S4, the ground-based successor to current CMB experiments, targets similar precision goals. Better measurements of the proton lifetime from upgraded underground detectors will constrain the proton decay requirement. Better measurements of the Higgs vacuum stability from future collider experiments will constrain the mass disappearance requirement. The theory is making contact with experiment. The results are not yet conclusive. And yet the question refuses to go away regardless of whether CCC survives experimental scrutiny. The question of why the universe began in such an absurdly improbable state, why the Big Bang started in a 1 in 10 to the 10 to the 123 configuration, why the thermodynamic arrow of time points in the direction it does, why we live in the structured, complex, star-filled middle of cosmic history rather than in the featureless equilibrium that most of the universe's timeline consists of. These questions do not have satisfying answers in the standard cosmological framework. Inflation explains the smoothness of the CMB. It does not explain why the pre-inflationary state had the right properties to produce the inflation we observe. The Standard Model explains the masses and interactions of fundamental particles. It does not select initial conditions. The question of why this universe, rather than some other universe, exists in the state, it does remains genuinely, stubbornly, embarrassingly open. CCC offers an answer. It may not be the right answer, but it is a real answer, in the sense that it is mathematically precise, physically grounded, and empirically constrained. Even if it is eventually falsified, even if Lightbird finds no Hawking points and proton decay experiments keep coming up empty, and the Higgs vacuum turns out to be absolutely stable, the framework will have advanced the conversation. It will have transformed the initial conditions problem from a vague philosophical discomfort into a specific geometric question with a specific geometric answer that can be tested and, if wrong, ruled out. That is not nothing. In the history of physics, the theories that got the right answer to a question that no previous theory was even asking precisely have often been the ones that changed everything. The radiation in your room right now is, at minimum, the oldest observable thing in our universe. 13.8 billion years of uninterrupted travel, carrying the direct imprint of conditions 380,000 years after our Big Bang, unmodified by anything that happened in between. Whether it carries anything older than that, whether buried in the temperature fluctuations of the CMB, there are circular whispers of black holes that evaporated in a universe that preceded ours, is a question that is, at this moment, genuinely unanswered. The universe may not end in silence. It may end in a handoff, clean, geometric, inevitable. The way a flame moves from one candle to the next. Not the same flame, not a copy of the flame, but a continuation enabled by adjacency and the right conditions, requiring no mechanism beyond the geometry of the transfer itself. And somewhere in the unimaginable future of our universe, long after the last star has gone dark and the last black hole has finished its slow evaporation and the last photon has redshifted to an energy that is effectively zero, a conformal surface is forming, quietly, inevitably. The boundary between our story and the next one. The ending that functions as a beginning. The death that is, from the other side of the geometry, a birth. Roger Penrose may be wrong about the details. He is almost certainly right about the question. And in physics, as in most things that matter, asking the right question precisely enough is more than half the work. The rest is waiting for the data.